Welcome back to the channel. Today, we're unraveling the intricate and fascinating structure of the universe, starting with the atom, the fundamental building block of matter. Then, we'll take an in-depth look at the standard model of particle physics, a framework that describes the fundamental particles and forces that govern everything around us. Buckle up for a journey through the very fabric of existence. Part 1. The atom, a complex foundation of matter. The atom is the foundation of all matter. However, atoms themselves are incredibly complex systems made of subatomic particles and governed by fundamental forces. Let's break it down further. Subatomic particles. At the core of the atom are protons, neutrons, and electrons. But each of these particles has distinct properties and roles in the behavior of atoms. Protons located in the nucleus of the atom. Protons are positively charged, +1, and determine the atom's chemical identity. The number of protons in the nucleus defines the element's atomic number. For example, carbon has 6 protons and oxygen has 8. Protons are made of smaller particles called quarks. Neutrons are electrically neutral. Charge equals 0, and also reside in the nucleus. Neutrons have a crucial role in stabilizing the atom. Their number, combined with protons, determines the isotope of the element, e.g., carbon-12, carbon-14. Neutrons also consist of quarks and experience the strong force that holds the nucleus together. Electrons are negatively charged. Charge equals -1. And orbit the nucleus in discrete energy levels, or shells. Electrons govern the atom's chemical behavior, determining how atoms bond with each other to form molecules. Their wave-like properties and quantum behavior challenge classical physics. Forces within the atom. The forces that act within the atom are fundamental to its structure and stability. Electromagnetic force, responsible for the attraction between protons and electrons. It also governs the interactions between atoms and molecules, defining chemistry. Strong nuclear force. This is the strongest of all the fundamental forces and is responsible for holding protons and neutrons together in the nucleus. It acts only over very short distances, but is incredibly powerful. Weak nuclear force, responsible for radioactive decay and certain nuclear reactions. The weak force is pivotal in processes like the fusion reactions in stars. Part 2. The standard model of particle physics. Unveiling the building blocks of the universe. The standard model of particle physics is the theory that describes 3 of the 4 fundamental forces of nature: electromagnetic, weak, and strong forces, and the fundamental particles that make up all matter. The standard model is incredibly powerful, yet it leaves gaps, like the mystery of gravity. Fundamental particles. The standard model categorizes all known elementary particles into 2 main families: fermions, which make up matter, and bosons, which mediate forces. Fermions. These particles form the matter in the universe. Fermions include quarks and leptons, and they obey the Pauli exclusion principle, meaning no 2 fermions can occupy the same quantum state. Quarks. Quarks are the fundamental constituents of protons and neutrons. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom. Quarks always combine in groups, either forming pairs like up and down quarks to form protons and neutrons, or more complex structures. Leptons. Leptons include the electron, which orbits the atom, and neutrinos. Electrons are the most well-known lepton, but neutrinos are incredibly light and interact only weakly with matter, making them difficult to detect. Bosons. Bosons are force carrier particles that mediate the fundamental forces of nature. Photon. The photon is the force carrier of the electromagnetic force. It is massless and allows for the transmission of light and electromagnetic radiation. Gluon. Gluons carry the strong force, holding quarks together inside protons and neutrons. They are responsible for the stability of the atomic nucleus. W and Z bosons. These particles mediate the weak nuclear force, responsible for radioactive decay and nuclear reactions like fusion in stars. Higgs boson. The Higgs boson is associated with the Higgs field, which gives mass to other particles. Its discovery in 2012 at CERN provided experimental confirmation of a key piece of the Standard Model: interactions between particles. The forces within the Standard Model arise from exchange particles, and interactions between particles are governed by these forces. For example, electromagnetic force, mediated by the photon; strong force, mediated by gluons; weak force, mediated by W and Z bosons. The unification of forces. The Standard Model provides a framework where three fundamental forces, electromagnetic, weak, and strong, are successfully unified. However, it does not include gravity, which is described by Einstein's theory of general relativity. The quest to unify all four forces, including gravity, into a single theory called quantum gravity remains one of the biggest unsolved problems in physics. Part 3. The history of the atom. Discovering particles and forces. Early theories and discoveries. The concept of the atom has evolved over thousands of years. Ancient Greek philosophers first proposed the idea that matter was composed of indivisible particles. But it wasn't until much later that experimental evidence confirmed the existence of atoms and subatomic particles. Point 1. The discovery of the atom. Democritus. Circa 400 BCE, the idea of the atom was first proposed by the Greek philosopher Democritus. He suggested that everything in the universe is made up of small, indivisible particles called atomos, from the Greek atomos, meaning indivisible. However, this was purely a philosophical idea, and no experimental evidence was available at the time. John Dalton, 1803. John Dalton, an English chemist, is often credited with the development of the modern atomic theory in the early 19th century. His atomic theory proposed that all matter is composed of atoms. Atoms of the same element are identical in mass and properties. Atoms combine in simple whole number ratios to form compounds. Chemical reactions involve the rearrangement of atoms. That Dalton's theory laid the foundation for understanding chemical reactions and helped establish the idea of the atom as a fundamental building block. Point 2. Discovery of subatomic particles. J. Thomson, 1897. Discovery of the electron. J. Thomson, a British physicist, discovered the electron through his experiments with cathode rays. By applying electric and magnetic fields to the rays, he concluded that the rays consisted of negatively charged particles much smaller than atoms. He initially proposed a plum pudding model, where electrons were embedded in a positively charged soup. Ernest Rutherford, 1911. Discovery of the nucleus. Ernest Rutherford, a New Zealand physicist, performed the famous gold foil experiment, which led to the discovery of the atomic nucleus. Rutherford fired alpha particles at a thin gold foil and observed that most passed through, but some were deflected at large angles. This suggested that atoms have a small, dense, positively charged nucleus at their center, surrounded by mostly empty space. Niels Bohr, 1913. Bohr model of the atom. Niels Bohr, a Danish physicist, refined Rutherford's model by introducing the idea that electrons orbit the nucleus in discrete energy levels. Bohr's model explained the spectral lines observed in hydrogen and provided the first quantum mechanical treatment of atomic structure. James Chadwick, 1932. Discovery of the neutron. James Chadwick, a British physicist, discovered the neutron by bombarding beryllium with alpha particles and observing the emission of neutral particles. The neutron had nearly the same mass as the proton, but no electric charge. This discovery completed the set of subatomic particles. Point 3. The discovery of atomic forces. Coulomb's law, 1785. Electrostatic force. Charles-Augustin de Coulomb, a French physicist, formulated Coulomb's law, which describes the electrostatic force between charged particles. This force, which can either attract or repel, is fundamental in understanding the interaction between the positively charged nucleus and the negatively charged electrons and atoms. Coulomb's law states that the force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. Maxwell's equations, 1860s. Electromagnetic force. James Clerk Maxwell, a Scottish physicist, formulated the electromagnetic theory, which describes the interaction between electric and magnetic fields. His equations showed that light and electromagnetic waves are manifestations of electric and magnetic fields propagating through space. Albert Einstein, 1905. Photoelectric effect. Albert Einstein, in his 1905 paper on the photoelectric effect, explained that light can behave like a particle photon, leading to a quantum understanding of electromagnetic radiation. His work contributed to the development of quantum mechanics and helped confirm the theory of the electron. Erwin Schrödinger, 1926. Quantum mechanics. Erwin Schrödinger, an Austrian physicist, developed the Schrödinger equation, a fundamental equation in quantum mechanics that describes how the quantum state of a physical system evolves over time. This equation describes electron behavior in atoms, helping us understand the probabilistic nature of electron locations. Werner Heisenberg, 1927. Uncertainty principle. Werner Heisenberg, a German physicist, formulated the Heisenberg uncertainty principle, which states that we cannot simultaneously know the exact position and momentum of a particle. This principle is fundamental to quantum mechanics and challenges the classical ideas of determinism. Point 4. The strong nuclear force and quantum chromodynamics, QCD. The discovery of the strong force. 1930s to 1940s, the strong nuclear force was proposed to explain the force holding protons and neutrons together in the nucleus. It was understood that the electromagnetic force alone couldn't account for the stability of the nucleus, as protons would repel each other due to their positive charge. Quantum chromodynamics, QCD. 1970s. Quantum chromodynamics, QCD, was developed as the theory of the strong force. It describes how quarks and gluons interact, mediated by the exchange of gluons, the force carriers of the strong interaction. QCD is a central part of the standard model of particle physics, developed through the work of physicists such as Murray Gell-Mann and George Zweig, who proposed the quark model. Point 5. The weak force and electroweak theory. The weak force, 1930s to 1960s. The weak nuclear force was identified as the force responsible for processes like beta decay. In the 1970s, the electroweak theory unified the electromagnetic force and the weak nuclear force, showing that they are two aspects of the same fundamental force. Electroweak unification, 1970s. The electroweak theory, developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg, proposed that the electromagnetic force and the weak nuclear force are different manifestations of a single force at high energies. This theory was experimentally verified in the 1980s, leading to the discovery of the W and Z bosons at CERN. In conclusion, our journey through the history of the atom has taken us from ancient philosophical ideas to the cutting-edge discoveries of modern physics. Initially proposed by Greek philosophers like Democritus, the idea that matter is composed of indivisible particles laid the groundwork for centuries of scientific inquiry. John Dalton's atomic theory in the 19th century further refined this concept, asserting that atoms were the basic building blocks of matter and that chemical reactions were merely the rearrangement of these atoms. The discovery of the electron by J.J. Thomson in 1897 marked the first breakthrough in understanding the atom's internal structure, revealing that atoms were not indivisible, but contained smaller subatomic particles. This led to Ernest Rutherford's famous gold foil experiment in 1911, which showed that atoms have a dense, positively charged nucleus at their center, a discovery that reshaped our understanding of atomic structure. Niels Bohr's model of the atom in 1913 introduced the idea of quantized electron orbits, bringing together classical and quantum ideas. The 20th century continued to unveil the complexities of atomic structure. The discovery of the neutron by James Chadwick in 1932 completed the set of subatomic particles, while Schrödinger's wave equation and Heisenberg's uncertainty principle provided a deeper, probabilistic understanding of electron behavior. At the same time, the forces that govern the interactions of these particles came into focus. The electromagnetic force, described by Coulomb's law, governs the attraction and repulsion between charged particles, while the strong and weak nuclear forces, discovered through years of experimentation, were understood to govern the interactions within the atomic nucleus. The strong nuclear force binds protons and neutrons together, while the weak force plays a crucial role in radioactive decay and nuclear reactions that in the latter half of the 20th century. The standard model of particle physics emerged as a unifying theory, describing how fundamental particles interact through three of the four known forces: electromagnetic, strong, and weak, via the exchange of force carriers like photons, gluons, and W/Z bosons. The discovery of the Higgs boson in 2012 further confirmed the existence of the Higgs field, which gives particles mass and completes our understanding of how fundamental forces interact at the quantum level. This comprehensive exploration of the atom, its particles, and the forces at play not only highlights the monumental achievements of scientists throughout history, but also shows how our understanding of the universe has evolved. The study of the atom remains a fundamental aspect of physics and chemistry, influencing a wide range of fields from materials science to cosmology. As we continue to probe the depths of atomic and subatomic realms, new discoveries may offer insights that challenge and refine our current models, expanding our comprehension of the very fabric of reality.